I want to start today with words that just kind of appear, you know?
Out of nowhere.
Exactly. Like 10 years ago, if I said I was doom scrolling while waiting for an influencer to finish their prompt engineering,
You'd get a very strange look.
you think I was speaking an alien language, right?
Or having a very strange fever dream, yeah.
Right. But today, those are just normal words. Language is this living thing.
It evolves constantly. And for us, that's fine. We hear doom scrolling, we get it from the context, and we just move on.
Yeah.
But for a computer,
For a computer, that's a whole different story.
it's an absolute nightmare.
Because they're built on dictionaries, essentially, or databases that act like dictionaries.
Exactly, yes. Your AI models, your search engines, all of them.
Yeah.
They rely on these massive pre-existing vocabularies. So when you throw a word at them that they've never seen before, an unknown word, they hit
a brick wall. The computer says no moment.
It is. And the old solution is so painfully slow. You have human lexicographers, actual people trying to manually update everything.
Yeah. But the internet moves way too fast for that.
You can't hire enough people to catch every new slang term that pops up on TikTok.
So the holy grail is to get the computer to figure it out by itself.
To act like a detective. Which brings us, finally, to the research we're unpacking today.
Okay.
We're looking at a paper titled Combining Contextual and Structural Information for Supersense Tagging of Chinese Unknown Words.
That is a mouthful. But the core mission here is teaching a computer to see a brand new word and figure out what it means.
Without any human help. Specifically, to assign it something called a supersense.
Okay, let's pause on that word. Supersense.
Yeah, it's a bit of jargon.
It sounds like something from a comic book, My supersense is tingling.
Right, but it's not quite that exciting, unfortunately. In linguistics, a supersense is just a very high-level category.
A broad semantic bucket.
That's a great way to put it, a bucket. So if the unknown word is, say, iPhone, the computer doesn't need to know the model or the screen size.
It just needs to know which bucket to throw it in.
Right, so the supersense might be tool or artifact.
Got it. And if the word was Google, the bucket is organization.
Precisely. And if we can do that, we can slot the new word into a thesaurus, in this case the Chinese thesaurus Selen, and suddenly the AI knows how to handle it. It knows iPhone acts like hammer and not like Steve.
But the paper is specifically about Chinese, and I get the feeling Chinese plays by a very different set of rules here.
It really does. And that's the central drama of this paper. It's a battle between two different detective strategies. Context versus structure.
Okay, so let's start with the context team. This is the bread and butter for English AI, right?
It absolutely is. In the English-speaking world, we live and die by what's called the distributional hypothesis.
Which is a fancy way of saying.
You know a word by the company it keeps.
Okay.
Let's try an experiment. I'm going to make up a word. Let's say glump. You've never heard it before.
Definitely have not heard glumph.
Okay, but if I say I use the glump to eat my soup, and then I say I put the glump in the dishwasher next to the fork, what is a glump?
It's a spoon, or I don't know, a spork or something. It's a utensil.
Exactly. You didn't know the definition, but you saw it hanging out with soup, eat, and fork. The context gave it away. This works incredibly well for English.
So you would think, logically, this should work for Chinese, too.
You would, and researchers did. But when they tried these standard context-based methods on Chinese unknown words, the results were, well, they were catastrophic.
How bad are we talking?
We are talking about an accuracy rate of around 34%.
34%. That's barely better than random guessing. It's basically useless.
It's a failing grade. And the reason comes down to the fundamental architecture of the language itself.
So why does the glumph trick fail so badly in Chinese?
Let's think about the English word person. P-E-R-S-O-N. If I take the letter P, does that mean human?
No, it's just a sound.
What about E or R?
No, of course not. You need the whole word for the meaning.
Exactly. The individual pieces don't carry meaning. But Chinese is different. Chinese words are made of characters, and those characters are often morphemes. They carry their own meaning. Take the character min, M-I-N. That character, by itself, literally means people or person.
So if I see a new complex word like jimin, and I see that min character inside it, I already have a huge clue.
A massive clue. It's probably related to people. That is structural information. You're looking at the anatomy of the word itself, not just its neighbor.
Okay, so we have two teams. For English, outside context is king. For Chinese, inside structure is king.
That's the setup.
So I'm going to be Captain Obvious here for a second. If context is so bad for Chinese and structure is pretty good, why not just use structure or, both?
Well, that is the million-dollar question.
Yeah.
And they did try using just structure. That got them to about 60% accuracy.
Better, but still not great.
Right, because it's too rigid. Sometimes the character is used metaphorically, so they try to combine them.
And their first attempt, what's called a loose coupling strategy, it failed.
Loose coupling. Sounds like a bad relationship status.
It kind of was. Here's how it worked. First, they used the structure method, looking at the characters, to generate a list of possible meanings.
Okay, so the structure says this word has min in it, so it's probably a person.
Right. Then they handed that list over to the context method and said, okay, now you rank these and pick the best one.
And that didn't work. Why wouldn't a second opinion help?
Because the second opinion was incompetent. Remember 34% accuracy? The context method for Chinese is so noisy and unreliable that it essentially takes the good structured list and just scrambles it.
So you're giving a well-researched report to a toddler and asking them to make the final decision.
That's the perfect analogy. The loose coupling failed because the second half of the team had no idea what it was doing.
Okay, that makes perfect sense. So this paper is about finding a better way to make them work together.
Precisely. Enter tight coupling.
Which means what exactly? It means you don't treat them as two separate sequential steps. You have to use the structure, the internal meaning of the characters, to actually teach the context method how to be smarter.
You're using one to guide the other.
You're using it to bias the system. The researchers' core assumption was the more characters two Chinese words share, the closer their meanings are likely to be.
Okay, let's break this down then. The paper outlines a 4-step process for this tight coupling.
Right. Step 1 is the filter. They build what they call a candidate synonym set.
So we take our unknown word, let's use their example, Jimin.
Right, G-min. In the financial news data they used, it means stock fund investor. But the computer doesn't know that.
So it looks at the structure, it sees the character min.
And it scans a whole thesaurus for other known words that also contain min. And it finds shimin, which means citizen.
So Shimin becomes a candidate, a potential cousin.
Exactly. They also filter by part of speech, so nouns only get compared to other nouns. Now, instead of comparing our word to the entire dictionary, we have this small, curated list of likely relatives.
Okay, step 2. Contextual similarity computation. This is where we look at the sentences, right?
This is where we go back to the giant news corpus. They pull thousands of articles and find every sentence where our unknown word, jimin, appears. And they do the same for his cousin, shimin.
And they compare the neighborhoods the words live in.
Correct. Let's switch to their other example. Gong'anju Zhang. It means police chief.
Okay, Gong'anju Zhang.
The system finds sentences with police chief and notices words like become or serve as often appear right before it.
Like, she will become the new police chief.
Exactly. Then it looks at a candidate like Hui Zhang, which is chairman, and it sees you can also become chairman or serve as chairman.
But you probably wouldn't serve as a toaster.
You would not. So the system sees that the context for police chief and chairman is very similar. It even counts the frequencies.
But this is the part that usually fails. So what's different this time?
Step 3. This is the secret sauce. Lambda weighting. This is the tight coupling in action.
Lambda weighting. Okay, what's actually happening here?
You can think of lambda as a trust meter. The system gets a similarity score from the context part. But before it accepts that score, it double-checks the structure. It asks, how much do these two words actually look alike?
So it's using the visual match to adjust the score.
Yes. And they have specific rules. If the unknown word and the candidate share both the first and the last character, that's a huge structural link.
Like their example, Dianji Chang versus Dian Ki Chang.
Exactly. One is electronic appliance factory, the other is electronic motor factory. They both start with Dianin for electronic and end with Chang for factory.
They're practically twins.
So the lambda weighting kicks in and says, these two are twins, I'm going to boost their similarity score. I really trust this match.
And what if they're not so similar?
If they only share one character like Jimin and Shimin, the system says, okay, they're related, but it's not a slam dunk. I'll just give this a standard weight.
I see. So it's using the strong part, the structure, to tell the computer how much to trust the weak part, the context.
It's a correction mechanism. It stops the noisy context data from leading the whole system astray.
That's really clever. And what's the final step?
Step 4 is the vote. They use a K-nearest neighbors classifier, or KNN.
KNN. I've heard of that, but isn't that usually for, like, image recognition?
It's used for a lot of things.
Oh.
Imagine you don't know what kind of neighborhood you live in. You look at your 3 closest neighbors. One's an architect, the second is an architect, and the third is also an architect.
I'm probably in an artsy, design-focused neighborhood.
Exactly. The system looks at the top-ranked candidate words after that lambda weighting. If the top 5 neighbors are all tagged with the supersense person, the system votes and decides, okay, our unknown word must also be a person.
So after all that, the filtering, the context checking, the trust meter, the voting, did it actually work?
It was a massive success. The proposed method outperformed the best context-only method by about 25%.
25%. In AI, people usually get excited about a 1 or 2% improvement. That's a huge jump.
It's a generational leap. And it beat the best structure-only method by about 10%. But here's the number that really blew me away.
Go on.
They calculated the top line, the theoretical maximum accuracy possible, and it was near 98%.
98? What does that even mean?
It means that step 1, the filtering step where they just look for character cousins, is incredibly reliable. It suggests that in Chinese, just looking at the characters gets you the right answer 98% of the time.
Wow. So the cheat code is real. If you ignore the characters in Chinese, you are fighting with one hand tied behind your back.
Absolutely. But there was one other little surprise in the results, more for the data science nerds out there.
Ah, right. The part about the math they use.
Yes. Normally, in information retrieval, the undisputed king of algorithms is TF-IDF, term frequency inverse document frequency.
That's what search engines use, basically.
Historically, yes. It's great at finding keywords because it loves rare words.
But it didn't win here.
No, it actually did pretty poorly. The winner was an algorithm called PMI, or Pointwise Mutual Information.
And why is that? Why would the search engine king fail?
Because we aren't trying to find a unique document. We're trying to find a relationship. TF-IDF looks for the needle in the haystack, but PMI measures magnetic attraction. It measures how much 2 words stick together more than you'd expect by chance.
So for finding synonyms, words that can swap places, that stickiness is what really matters.
That's the theory. And they found other weird things, too. It just goes to show you can't just copy-paste algorithms from one problem to another. Supersense tagging is its own unique beast.
Which I think brings us to the big takeaway here. We started this by talking about how language evolves, and dictionaries are always playing catch-up.
And this research shows we might not have to wait for the dictionaries anymore. We can build systems that evolve with the language.
And this is the big, but only if we respect the DNA of the language itself.
Correct. You couldn't just take this method and apply it directly to English.
Because our letters, P-L-U-M-B-E-R, don't have a tiny symbol inside that means human.
Right. English is opaque. Chinese, at least structurally, is transparent. The characters are like a metadata layer baked right into the language.
That's a great way to put it. The history is encoded in the strokes.
By respecting that internal structure, the computer gets a head start that it just doesn't get with English.
It really makes you think about the future of AI. We always assume English is the default language of technology.
It's the bias we all operate under, for sure.
But this research hints at something really provocative. If a language like Chinese has these built-in cheat codes, if the characters themselves can tell the AI, I am a tool or I am a person, does that mean AI might eventually understand Chinese better than it understands English?
I think it's very possible. English is so messy and ambiguous. It relies so much on context. Chinese offers this elegant, structured roadmap right inside the words.
In the race to build a truly intelligent AI, having a language that explains itself might be the ultimate advantage.
I definitely wouldn't bet against it.
Well, that is a lot to think about. Next time you see a brand new word online, just remember there's an AI somewhere trying to put it in the right bucket.
And hopefully it's looking at the structure.
Thanks for listening to The Deep Dive. We'll catch you on the next one.